Hello and welcome again this Friday to the Tower. My name is Antonio Flores and today we are going to speak about a very interesting topic, that is artificial intelligence. Artificial intelligence is a scope for many words, so you may have heard about machine learning probably. You may have heard about deep learning. And you may have heard a lot of news and a lot of concepts regarding artificial intelligence. So today I have prepared some slides, some pictures to show you how artificial intelligence works, what is it really, and what can we find in the market. Okay, so like always, I suggest that you subscribe to this channel. It's very easy, and it's a nice thing that you can do to support this channel. We are doing this for free, so I'm here every Friday at 8 p.m. in Europe, 7 p.m. in the UK, and 2 p.m. East Coast, New York, on the East Coast, and 11 a.m. in the West Coast in the US. Okay, so maybe you are watching this video not live, maybe some days after we are meeting today, but for those that are live, I recommend that you write on the chat if you have any comments, if you have questions, if you want to share anything related to these topics, to the topic of today, artificial intelligence. You are free to do it, and I will be glad to hear you. And also, again, I remember that this is my website, this is my personal website, and you can contact me there as well. Okay, there will be information about me, about my books, about my work regarding technology, and I also share here in Twitter some news about this channel, about the tower, and about any other news that I find interesting. So, having said that, let's move forward to the topic of today. It's about artificial intelligence. We are speaking about artificial intelligence, and I said before, machine learning, deep learning, and other concepts related to this umbrella concept of artificial intelligence. Okay, what is artificial intelligence? Let me share. Let me speak about artificial intelligence. I have prepared a presentation, but it seems it's not working well today. I made some tests, but honestly, I should see. Okay, now I see it's going to be much easier than I thought. Let's start with the first slide. As I said, artificial intelligence is everything related to the ability of machines that perform any advanced tasks that are traditionally done by humans. Okay, so artificial intelligence is everything, is everything and it's nothing. You will find many people calling artificial intelligence to many things. You will find a washing machine with artificial intelligence, or maybe any basic instrument that is claimed to have artificial intelligence. Inside that, a more advanced concept is machine learning. And machine learning is more recent concept. So it started in the research many decades ago, but it's a concept regarding what we are going to see today. Is a technology based on a new concept that you will hear now and a lot of times along this presentation is called neural networks. Neural networks are artificial structures. It's software, it's something that is coded in software that replicates how the brain works. Okay, and this is quite more advanced technology to perform artificial intelligence and real artificial intelligence in terms of understanding the environment, understanding things, making decisions, a lot of things that we will see later. And inside machine learning, you have as a part of machine learning, you have deep learning. What is deep learning? It's a very basic concept once you understand what neural networks are, but the idea is that deep learning is much more advanced machine learning in terms of infrastructure, architecture, computing power. So it's adding more to the existing concept of machine learning, and we will see it later on. Okay, so this is the concept of artificial intelligence, is the ability of a computer to perform tasks that are normally associated with human intelligence. Okay, it's about thinking somehow, or maybe taking decisions that are normally typical or exclusive from humans. This is traditional artificial intelligence. What is an expert system? You have it here. Traditionally, and let me speak about a bit about expert systems. So in the past, you can think of 1980s, 1990s, maybe. Computers were very slow, were very limited in capacity, in computing power, in storage, in the ability to process data. Normally digital data was text, maybe images, that's it. And one concept that was very trendy in these decades is the concept of expert systems. What are expert systems? And let me get back to the picture. An expert system is simply a database, is the knowledge base here in green, that is fed manually by an expert doing a specific task. Maybe it's an expert in managing an engine or a factory equipment, or maybe it's an expert doing some cooking recipe. This expert programs, codes a knowledge database, so is the rules that the computer will follow to guide another user that is not an expert. So it's something like first do this, then do that. If this happens, then do that. If the temperature is above this level, press this button. This kind of things is what expert systems are. It may become very complex, thousands of rules in the knowledge base to control a complex system. Okay, but the problem of these systems is that we need a human on the right side. So it's not true. It's not a true intelligent system. It's a system that compiles information from a human and then delivers the different options according to certain rules and certain parameters to another user. This is the origin of artificial intelligence. Then we have machine learning. And what is machine learning? Machine learning is a structure, again, a software, a computing algorithm that is able to learn from samples or from the environment. How is that possible, you may ask? And let me show you how the brain works, because neural networks, machine learning, everything is highly related about how the human brain and any brain in nature works. You know that brain is composed by neurons. You have here a picture of a typical neuron. The neuron is the brain cells. So brain cells are very strange, are different from any other cells in the body. And they have this particular structure. So they have a core here in the center. Then they have a very long tail, and then they have sensors around the core. You can see these branches around the core. These are called dendrites, and they are sensors, so electrical sensors indeed. So if there is any other neuron firing on the right side, you have the output, you have the axon terminals. The axon makes an electrical discharge to the environment. So it's like a small lightning, we can say. And one neuron fires a lightning through its axon, and then the other neurons around it will perceive this electrical stimulus by the dendrites, the input. Okay, it's very simple. Is you do something in the core, and then regarding of what happens with the stimulus, with the input, you provide an output or not, or a more powerful output, a more powerful electrical discharge, or more or weaker electrical pulse. Okay, this is the how a neuron works. It's incredible that you can think that the brain can create such complex thoughts, and the imagination, the decisions, everything is done by such a simple structure. But it's true. The art of the brain is that there are millions, hundreds and thousands of millions neurons all connected. And here we do, in the lower of the screen, you see what is an artificial neuron. An artificial neuron is what you see below. Is something, is a software, is an algorithm that has inputs, x1, x2, x3, etc., all the inputs that you want, and then it does some calculations in the core, in the center, and then provides an answer, y, on the right. Okay, and then it's important that we speak here about the activation function. What is the activation function and why it is important? The activation function is how the output of the neuron is built regarding the inputs. Okay, so maybe let me show you the next slide. The activation function can be on-off, is the first one, you have it here. So the first one is step function, is if I receive inputs, and for example my core does adds up of all the inputs, so 1 plus 2 plus 3 input, and this is below a threshold, let's say 5. So 1 plus 2 plus 3 is less than 5, then the answer is 0. And if it's above 5, then the answer is 100%. Okay, so that's the step function. It's like a switch. So you switch on the light on a room, in a room, or you switch it on. It's not anything in the middle. Other activation functions can be more flexible or smoother, we can say. So it can be linear, it depends. So let's sum all the inputs and then provide just the sum of all inputs will be the output. So if the sum is 3, the output will be 3. If the sum is 2, the output will be 2. It can be linear. Okay. One interesting activation function is the logistic, the third one. Logistic function is important. What is the logistic or the logarithm? The logarithm function. Why it is important? Logarithms are complex to calculate by computers, but logarithms is the way nature works. Okay, so when you feel pain, you feel pain under a logarithm scale. When you hear noise or any sound, you hear it in a logarithm scale. When you see through your eyes, you see the light in logarithm scale. And what is logarithm scale? Logarithm scale is a scale that goes with very detail when the value is very low. So between 0 and 1, you can measure it very precisely, very accurately, but it goes flat, nearly flat, when the values are very high. And for this reason, you are able to listen. For example, when some person whispers to your ear, you can hear it. And if this person speaks louder, then you need to move apart because it's too loud. But when you are in a music concert, for example, then the music is very loud, is too loud, is in the upper scale of your ability to listen, to hear, and then a minimal variation, you don't perceive it. Okay, so if the power decrease is the noise or the sound decreases its power 10% or 20%, you don't perceive it. Okay, this is the way the nature works, and everything works the same. So you can think of cells, you can think of blood in your body, you can think of how trees use water from soil. Everything goes under this activation function. So it's very interesting to do an exact copy of a real neurons, because real neurons activation functions are logarithms, are sigmoidal or logistic, whatever is variations, but the essence is the same. But as I said before, the problem is that logarithm is a very complex mathematical operation, and it requires a lot of computing power. So if you have to do millions of logarithm operations per second, then you have a problem, because you will need a very strong computer to be able to do that. What do we do instead? We use normally in artificial neurons the rectified linear function. That is, if the answer, if the output, if the calculation is below 0, the answer is 0. So we don't provide negative answers. The answer is nothing. Okay, so the neuron does nothing. And then if the answer is, if the calculation is above 0, then you provide a linear activation. So you can say, okay, this is too low, is little, medium, max, extra max. You can do some grade in the output of the neuron, and it's better than the step function that is too simple. Then if we move forward, you have the idea of the perceptron. Perceptron, what is the perceptron? We show the perceptron here in 2 slides before. The perceptron is this one, okay? Is the one on the bottom left of the screen. Is a simple artificial neuron. Is just like that. Somebody called it a perceptron, and this is a very good looking name, and it remained that way in the literature for decades. The perceptron can do is one single neuron, so it can do a very simple calculation. But it's good, for example, for classification of different data. We have here some data in a matrix in 2 parameters, and the perceptron can decide according to the line that you see in the middle. Okay, if you are above the line, then you are blue. If you are below the line, then you are red. And it does some kind of intelligence. Very limited, in fact, is useless in practical applications. But theoretically, it was the how neural networks, how machine learning was born. The truth is that we need more complex ecosystem, and we need what we call the multi-layer network. And this is a network composed by artificial neurons, by perceptrons. So here you have 4 perceptrons in the first layer. Is the layer that is connected to the reality, to the input, to the physical world, to the data, whatever. And then in these neurons are connected to a second layer of 4 additional neurons. This is an internal layer, so they receive inputs from the outputs of the previous layer. Then we have a second internal layer, so it's the third layer with 3 neurons. And then we have the output. The final layer is the 4th layer, that these neurons will activate something. So will give the answer to a problem, will activate, will draw a pixel in an image, will produce a sound, will activate a remote control of a device, anything that is a real output for the environment or for us. Okay, this is what we call a multi-layer network, and this network has the ability to understand or perform some more advanced tasks, as you may imagine, than a single perceptron. Okay, then let's speak about overfitting, underfitting, generalization, regularization. Okay, what's this? These are probably too complex concepts for today, but I just wanted to speak about them because the concept of fitting is what you have in the picture on the right. Okay, let me put it a bit larger. So the picture on the right has samples of, again, let's assume that they are parameters measured from reality. The parameters, for example, let's say that red dots are people living abroad, and blue dots are people living inside the country. And then we have represented here the salaries, for example, of these people, and also you have 2 axes. One axis is the salary, another axis is the age, for example, of that person. And then we want to understand if I tell you my age and I tell you my salary, you tell me, the artificial neuron will tell me, okay, you are in your country or you are abroad. And for that, the neural network needs to build a function that is the line that you see in black or another different line that you see in green to the side. So if it's above the line, then it's blue, then you are in your country. If it's below the line, then you are red, you are outside, you are abroad, you are outside your country. How does it, the neural network? Okay, you have to believe, it can be justified mathematically, but we will not do that here today for sure, because it would be crazy. But you need to know and to believe that neural networks produce nonlinear functions. What is a nonlinear function? Okay, a linear function is a function that is proportional. For example, if you give me 2, I give you 4. If you give me 4, I give you 8. If you give me 6, I give you 12. Okay, I give you double than what you give me. This is a linear function, is double, triple, whatever. Non-linear functions are functions that can do things much more complexly. Okay, so complex as the green line that you see here. So it does some complex calculations and it's able to say, okay, this person in this point is blue or is red, and builds an algorithm that is able to decide very complex scenarios. The problem with that is that neural networks can do both approaches. Okay, can do a more linear approach, is the black line is more or less simple. Okay, it's very simple to calculate, or it can do a green approach. The green line approach is very complex, and maybe it's nonsense, because maybe the people that are red above the black line are exceptions, so it's not representative. You know what I mean. So this is what we call overfitting and underfitting. So neural networks learn from samples, from having the inputs, then adjusting the internal structure of the network, and then producing the output. If you give an input, then the neural network learns. So if you are classifying, for example, in the same example, if you say, okay, John lives in the US and this is his salary, and this is 43 years old, then the neural network, it says, okay, I put him in the blue group. Blue group is the activation function for blue group is on top. The activation function for red group is 0. Okay, so this person is in the blue group. If you feed another person, the neural network will understand how to place it in the blue or in the red group. But the problem is that maybe it's not so complex. So maybe Young lives in the US, is 43 years old, and his salary is, I don't know, 50 grand per year. But maybe Mary is in the US, is 43 years old, and his salary is 45 grand, and it's also blue. So you know that it's not easy to understand how reality works for a neural network. The same that is not easy for us. So we have to see a lot of examples to learn, to see samples, to have data. So one person, one kid is receiving inputs to his brain since the moment he or she is born. So a lot of dozens of millions of inputs to perform some thinking, some rules in your brain. And the same happens to neural networks. So maybe in the beginning they are underfitting because they will see, okay, this person is blue, this person is red, so if somebody comes with more or less this way, this is blue, but with time this network will realize that the reality is much more complex and will try to draw the green line. The problem is that this green line may be too precise to the sample, to the data that you are processing, but it's not the reality. Maybe you are biased. You are receiving a lot of samples from one side or from one group or whatever, and you are biased. So this is a risk also of the neural networks, the same than humans. Okay, you may be biased because you always saw this pattern in the people, but it's not reality. The same can happen, and this is what we call overfitting. So you are fitting too much to the samples. You are not representing the reality. Probably reality is more simple. Is not so complex to fit all the samples that you are watching. Maybe there are some exceptions that you should discard from these samples, and you should pay attention to another data that you are not feeding in your network. Okay. Then another concept regarding neural networks is generalization. Okay, generalization is very important because, as I said before, is what we do, what we humans do when we think. We cannot analyze millions of cases to give a conclusion. We have to be able to provide an answer with the data we have. So even if you are 5 years old, you have to provide an answer. If you think that something is dangerous, then you decide that this is dangerous and you do some things. And if you think it's not, then you do different things. But you decide with the information you have. Maybe a 5-year-old boy has very little information about what is dangerous and what is not, but he does a decision every time. And this is the same characteristic is for neural networks, artificial neural networks. So if you feed one network with data, it will give you an answer. It may be right or maybe wrong, or maybe more or less right or more or less wrong, but always it will give you an answer. For example, if you build a neural network to analyze a picture and say, okay, is this a cat or is this a dog? This is a classical example, okay, in the literature. The neural network will always say to you, this is a cat or this is a dog, or this is 90% a cat or 90% a dog, or 85 or 60 or whatever. But it will always say something, okay? So if you feed the network with a picture of a horse, the neural network will say something, okay? It will say, okay, this is more like a dog. It's a dog, okay? Because why? Because there is no option to this network to identify a horse, because it never saw a horse before, but it will say something exactly like a person, okay? And then regularization is the third concept. Regularization is a way to do to provide data that is homogeneous, that is readable. So you do something that is more or less understandable by the neural network. So you want to analyze, for example, dogs and cats, and then you feed the network with different pictures of dogs and cats. You don't start feeding turtles, horses, all kind of animals, even a plant, even a person. You don't do that, because then the neural network during the training phase, and we will see it later, during the training phase it will get mad, exactly like a person, okay? You have to be careful with the rules, with the data that you expose the network to. Okay, so one important question, I wanted to add this slide. Here in this picture we work in 2 dimensions, in 2D, but obviously complex neural networks work in 3D, 4D, 5D, even 20 dimensions. It's endless. Okay, you cannot understand that with the human brain, but neural network are endless. Is software, so you can do all the dimensions you want to add. They can understand, for example, the 3D space plus time, 4D plus temperature, so 5 plus humidity plus the infrared spectrum plus whatever. So you can feed one neural network with all the data you want, much beyond the human sensors, the human senses that we are accustomed to. Okay. Let me explain now about deep learning. What is deep learning? Deep learning, as I said before, is a subset of machine learning that uses multiple layers in the neural network to expand its power. So we saw before 2, 3 layers, we can add 5, 6 layers, and maybe we can have much more neurons instead of 3, 4, 2 neurons we saw before in one layer. We can have 500 neurons per layer, 1000 neurons per layer. It's crazy. Deep learning is more related to technology than science. Okay, it's the same approach, the same concept, is the same theory behind deep learning than machine learning. The only difference is that machine learning could work in the early century, so probably in the late 90s. I was doing some simulation in the 90s at the university with neural networks. But if you want thousands of neurons with 7 internal layers in an architecture, then you need a huge power coming from computers or from GPUs. We will see it later. And it's called deep learning. So it's growing the computing power. It's as simple as that. Many people like to speak about deep learning, but it's not something more than increasing the power of the network. Okay, here we have a typical deep learning or deep neural network, or what is called deep learning. This network has more or less this structure. You can imagine, you see how each neuron is connected to each other in the next layer. So it's crazy how the amounts of connections grow as you introduce new neurons or layers in the architecture. And you can think of the amount of calculations and data processing that is needed to read and compute what is happening in each part of the neuron with a computer. Okay. Here you have some configurations. Let me show it bigger. These are typical neural networks. Each one was given a name in the literature. It's not relevant for now, for you to know at the moment, but it's good to know that you can have different architectures. So you have architectures that are decreasing the networks, for example, on the right side, top right, or then decreasing and then increasing, or then increasing, or you have a network that is sequential. So first layer, second layer, third layer, or you can have circular networks in the bottom. So there is a huge field of research regarding the optimal architecture, because the truth is that we don't know the neuronal architecture of our brain. So we don't know if our brain has neurons working in parallel, in circles, sequentially in different sequential layers, if they are networks. In the bottom right, you can see lines that connect networks not with only with the next layer, but with some layers below, before or after this layer. So it's feedback neurons. So it can be anything, and this is one major problem about machine learning and about deep learning, especially. That is, what do? Do we just increase the number of neurons? Do we just increase the number of layers? Do we do additional connections, feedback connections? Do we change the architecture? What is the best approach? And the truth is that we don't know. We have very limited knowledge yet about the architecture for a neural network. And this is something that will change in the future the power of artificial intelligence, because as more architectures are found for specific use cases, for specific applications, more power we will find in artificial intelligence compared to humans. And let me explain a little bit about the architecture. This is a slide that is intended just to show how to configure the architecture of a neural network. The first concept we understand is what we call the parameters. Okay, is in the middle of the figure. You see the parameters. What are parameters? Parameters are what the calculations done by each neuron. Okay, in the beginning of this session today, we spoke about adding up using the sum function for adding up the inputs. Okay, input 1 plus 2 plus 3, or maybe we can define a parameter, for example, twice the first input plus 3 times the second input plus the third input. These are the parameters. Okay, you define what calculation are you going to do with the inputs in a single neuron. Okay, these are the parameters. Can be the complex you want or the simple you want, but this is the way one single neuron works. On top of that, we have a very interesting concept that is called the hyperparameters. What are the hyperparameters? The hyperparameters are the parameters used to configure the neural network. For example, how many hidden layers? How many neurons in total? What is going to be the activation function? Are we going to use matrix, two-dimension, or tensor, 3-dimension, 4, 5, 6-dimension calculations? Is called convolution. Convolution is a specific method used in the calculations when we connect the neurons. Okay, but for the moment, just think that hyperparameters decide about the configuration of the whole network. So we have a lot of variables, a lot of possibilities to play with a single neural network. And we don't know what is the best approach. Okay, and then the other interesting point about configuring this neural network is that hyperparameters are much more important than parameters. Why? Because there is a feature of the neural networks called the convergence. And this is something prepared and created exactly as a replication of how the human brain works. What is convergence? Convergence is the way parameters, not hyperparameters, okay? Hyperparameters, you define it and you build the neural network. You cannot change it forever. The number of neurons, the activation functions, how many hidden layers. This is the brain, the architecture of the brain, the artificial brain. Is like our brain. We cannot change the number of neurons we have. We cannot change the brain configuration. We cannot attach one neuron to another. We cannot do that. Okay, we are born with our brain. Our brain grows, but this is defined by the creator. We can say that, but we don't change that with our thoughts. But what we do change along our life is precisely the way we think. Okay, since the moment we are born, we are perceiving stimulus, we are perceiving, analyzing data, and we are changing our parameters. Okay, so sometimes we say, okay, this is not so relevant. So why are you saying 3 times input 1, 2 times input 2, and one time once input number 3? The input number 1, it's not so relevant to get the conclusions, and we learned it as we receive more inputs and we do correct decisions, and we say, okay, input 1 is not relevant. Let's put 1 time input 1, but input 2 is more relevant for this conclusion. So let's put 3 times or 4 times input 2. And it depends on the data we see, we analyze, and on the inputs we have, if we get a correct, on the output, if we get a correct output or not. And this will change as long as data goes through the network. And this is precisely done with convergence in the artificial networks. Convergence is an algorithm that changes the parameters of the neurons individually, neuron by neuron. Okay, so you start first deciding the algorithm, the calculation for all neurons, but then there is an algorithm changing the weights and saying, okay, no, don't take this input into account, it's not relevant for this conclusion. To the other neuron, it can say, okay, this input is very important, so increase the weight, increase the parameter for this input. And this is the way the neural network evolves to an optimized state. We call an optimized state when the neural network is useful. It can classify or provide a good decision, or do an analysis, or analyze the inputs and provide a good output. And we call it the optimized state. And for that, the neural network has to evolve, like our brain. It has to evolve, changing the weights, changing the parameters in the neurons, in each neuron, to provide the right output. Okay. Then, I hope this is not too much for today. Okay. I think it's a very, very exhaustive explanation about neural networks, about machine learning, deep learning, all the topics. But I think that is the best way to understand how machine learning and deep learning works from a technical perspective. But if you are not too technical, maybe you can follow this. If you didn't to this point, let's summarize this part with maybe 2 concepts. One concept is the perceptron. So the perceptron is a single artificial neuron that replicates our neurons in our brain, and it gets some inputs, do some calculations, very basic calculations, some subtraction, multiplication, very simple, and then provides the output of this calculation. When you combine a lot of perceptrons, connecting the outputs of a perceptron as the input of the next perceptron, and then building a network, then you have a neural network. And this neural network can do much more complex decisions and much more complex analysis on the input data and provide output that is more high level, we can say. Okay, can you identify a cat if I show you a picture? So the input is the pixels of the picture, and then the neural network will do the calculations and it will say yes or no in the output. Is a cat or it isn't? And for doing that, we have mainly two important concepts. One concept is the architecture of the network. So we have to decide how many perceptrons, how many neurons we put in the network, how we connect one to the other, if we create layers or we put a circular approach or whatever, or feedback between one neuron and two layers before. We have to decide that, and this is not fully studied by far today. So there is a lot of room for improvement in the network architecture. And then something that is working automatically inside the network is the what we saw about the automatic configuration of the parameters in each neuron, etc., exactly how the brain works by observation. So as more input data you feed into the network and you tell, okay, right, wrong, right, wrong, right, wrong, this network will learn and say, okay, this is relevant, this is not relevant, this is combined, this is related to this one, so let's connect this network with this other, and then the connections will gain or lose weight, importance, relevance in the whole network. And this is the way we build intelligence artificially in an artificial neural network. And then let's move to the next part that is very interesting to know as well. Okay, it's let me get back to the presentation. Just 1 second. The functional types of machine learning and deep learning. What is that? We have seen what physical structures, we can call it physical, although they are code in software, but we can see it graphically. Okay, so this is the architecture of the neural network. Now we are going to analyze how the neural network can be configured. How can be, we can say, we start the engine of the neural network. We built a neural network by software, and then we say, okay, we have the inputs, let's see the outputs. We can do different approaches once we start the engine of the neural network. And this is what we call supervised, unsupervised, self-supervised reinforcement learning. Is the way the neural network learns. A neural network learns as long as it changes the parameters in the neurons. Okay, this is the way we learn. We change the parameters, the weight, the relevance, the neuronal paths in our brain. We change them, and then we have thoughts. This is the same way that we do in artificial neural networks. So supervised learning, you can imagine what is supervised learning. Is as simple as feed data to the network and then the network will say, here, for example, we show images of a dog, we show images of a cat, of different dogs and different cats, and then the neural network has an output neuron saying, it is a dog, and probability. Okay, in here in the example we feed a dog, a picture of a dog, and then we get the output of the network says it's a dog, 95% of probability. It's a cat, the rest, okay? All probabilities must add up 100%, okay? In this case, the neural network provides a correct answer saying it's a dog. So I'm 95% sure that it's a dog, is what the neural network is saying. But how does the neural network configure the parameters inside to show that answer, to provide that answer? So we do a supervised learning. We feed one picture, for example, of a dog, and then if the neural network says it's a dog, we say yes. If the neural network says it's a cat, we say no. And this information is fed back to the internal network to correct the parameters, okay? So we humans tell the neural network, you are right, you are wrong. You start with a picture, and whatever the neural network says, you say correct or you say wrong, and then the neural network acts by changing the weight to improve its answer in the next time. This is done hundreds, thousands, millions of times. So neural networks need millions of pictures probably, or at least 10,000 pictures or 100,000 pictures to be effective. Obviously, there is no human on the right side saying what the neural network, if the neural network is right or wrong. What we do is tagging the images. So we put a picture with a tag saying it's a dog, it's a cat, it's a dog, okay? And then the neural network, we put all the pictures in a database, and then the neural network takes the first picture, analyzes, and then says something, and then checks the tag of the picture and says, am I wrong or am I right? Okay, I'm right, okay, and then move the weights. This is the supervised learning, okay, is some kind of supervision, because in the end the tag of the picture was put by a human, okay, is clear, it can, or a human or a team. So we need tagged data to feed the network in a supervised model. We can say that this is a model that starts with defining the architecture, so building the model or setting the hyperparameters, you remember from the first part of this presentation. Then we train the network, is what we have just explained, so feeding pictures tagged with the result, and then the neural network can check, okay, was I wrong or was I right? Then we do some testing, okay, so we feed some pictures and we humans observe and say, okay, is giving a right answer or is failing too much? And once we decide that the testing are good, then we put it into production. But it's a linear approach. So in production, the supervised learning model doesn't learn anymore. So it's not like the brain works. The brain is continuously learning from the observation. Supervised learning has a training and then goes into production and does it the same way always. So if the neural network analyzes pictures and fails, it doesn't matter. This is not going to change the parameters anymore. Okay? This is supervised learning. Then we have unsupervised learning. What is unsupervised learning? Unsupervised learning is a neural network where you don't say anything about if the result is right or wrong. The neural network uses I don't know why, sorry, because I was speaking and I don't know why this slide was here. Okay, unsupervised learning is, as I said, where a network doesn't need a human input to tell her you are right, you are wrong, nothing. Why is that? Because we need tagged data, and tagged data or labeled data is expensive. We said before, we need humans doing the labeling, okay, in the beginning of the process. If we can feed raw data and labeled data coming from reality, it would be much better. Okay. The problem with unsupervised neural networks is the same that you can expect from an unsupervised baby. Okay. The baby will understand reality. He or she will make his own conclusions, okay, but you will never know if they are going to be right, wrong, or what kind of conclusions, okay. These networks get to the same results, and this is the reason why they are very good in clusterization. What is clusterization? Clusterization is identifying groups. So, for example, if I feed animals, pictures of animals into the network, to the unsupervised network, this network on time will get different groups of animals. First, for example, the network in the training process, the network will split animals with 4 legs, animals with wings, animals without wings or legs. Then it will separate, if we continue training the network with more pictures, it will separate big animals with 4 legs, small animals with 4 legs, birds, fish, I don't know, whatever. So in the end, the neural network will start making groups that are different from each other, but the network will never know if this group are mammals or fish or birds or whatever. There will be groups, group 1, group 2, group 3, group 4. It's the same that a human being would do if he was in nature alone without any society to learn from. And this is very good for some topics, as I said, clusterization. For example, in marketing, what clusterization is ideal for marketing purposes. So you can identify groups of consumers. You don't know if this group is called early adopters or this group are fashion victims. The neural network doesn't put names to this group, but it's possible. This network is able to identify this group, and sometimes this network identifies the group much better and can identify more groups than human beings, okay? Because remember, if you add power, if you add computing power, you have a more powerful artificial brain. And doing specific things, artificial networks do things much better than humans today, okay? So the way unsupervised artificial networks work is a bit complex for today, so we are not going any further with that, but just you know that artificial networks can be unsupervised and still provide useful information. And then let's see what is called self-supervised learning. Self-supervised learning is when you have an unsupervised network that uses, let me show this, uses some information to validate that the network is right or wrong. Okay, so you don't need tags provided by humans. You use tags to check if you are right or wrong, but these tasks can come, for example, from an unsupervised network. And let me explain. And let me explain also why I put all these pictures on screen. A self-supervised network starts analyzing pictures of people, okay? And then it starts to identify groups, like an unsupervised network. So we don't tell anything. We don't say this is John, this is Clara, this is Anne, this is Mary. We don't say anything. This neural network works unsupervised and decides that this is a group, this is another group, or maybe if we continue training the network, it can identify one person. Okay, so split one group into many parts, many members, subgroups, and in the end find one person. But it doesn't know what it means, so it doesn't know if it makes sense to split a group further or not. So we feed the name of the person to this algorithm and say, okay, this is John, this is Peter, this is Mark. And then it's taken as an input. It's not taken to improve the results for the future iterations. It's taken as an input. So as an input, it says, okay, this is a picture of John and this is a picture of Mark, and then continues doing the classification. And this is the way, for example, your smartphone, if you have, I have an iPhone, so if I make a picture, the iPhone can directly identify if I am in the picture, or my wife is in the picture, or a specific friend is in the picture, and I didn't analyze these are my pictures, these are not my pictures. So this algorithm identified my face in an unsupervised way, okay, but in a moment the algorithm saw my picture attached to my name, for example, in my social media, and the neural network in my iPhone says, okay, this is Antonio, I'm seeing this is Antonio, and this is his LinkedIn profile, and it's called Antonio. So all the times I see this picture, this person in a picture, I will tag it as Antonio. And this is self-supervised learning, okay? It's like a hybrid between both. And then moving forward, reinforcement learning. Reinforcement learning is a special learning method for neural networks consisting of associating pain and pleasure or award to the result of the decision of the network. Okay, is the way we work as well. So humans work avoiding pain and looking for rewards, and this is exactly the same we do in artificial neural networks. So if the answer is right, we don't say this is right, this is Peter, or we say +1, -1. We provide positive feedback or negative feedback. We don't say what is the right answer. We just say positive, negative, okay? And this is used with typical examples in games, okay? This is the way we solve puzzles, we solve challenges that are related to, okay, you did it well, okay, or not, you didn't do well. And this is something that we also do to train the neural networks. Okay, let's move a bit faster. Then the last part of the presentation is about implementing a neural network. Before that, let me summarize what we have seen. We have seen the ways we train a neural network. A neural network can have a supervised training where we initially show the inputs and say, check the outputs and say, okay, this output is right or is wrong. Then we saw the unsupervised model and self-supervised as well. So these two models are based on continuous training. So we feed data and the network gets to its own conclusions. And we don't say anything. The only thing that we can say is, okay, you give me this output, let's take into account that this output is linked to this input. So if you show me my picture, I will say, I am Antonio, and you use it. But I won't tell you never, if you show me the picture of John, I will never tell you I'm not Antonio or I'm Antonio. I will tell you only I'm Antonio if you show me my picture, okay? And it's continuously learning, and this is something important. These networks are continuously learning and improving. And then finally we spoke about the reinforcement learning. It's a particular learning, and we are not spending too much time for that. Let's get to the final part of this presentation. We are late, so my idea was spending 1 hour here, and we are 1 hour 14, so we are at 3:14 in New York. We are 9:14 in Europe. It's time to finish this meeting, but I recommend that you stay until the end. We are going to see how to build a network, how in a practical way, not from a theoretical way, but in a practical way. The neural networks are built by coding, as I said before, and run obviously on hardware. What kind of hardware is needed? You can guess that we need to do calculations, we need to do the core calculations of the neurons, so we need to do maths. And for doing maths, we can use CPU, of course. So your CPU, the CPU in your computer can do very complex calculations. It can do sums, multiplications, but also it can do comparisons, sorting, a lot of complex functions. But for neural networks, normally it's much better to have GPUs. Why is that? Because GPUs, graphical process units, are normally used to show pictures in your screen, but they have very simple cores. They can only do probably sums, multiplications, and that's it. Sums, subtraction, multiplications, that's it. Very few additional functions, but they have a lot of cores. Okay, normally you have you see here a 9th Intel i7, normally 4, 6, 8 cores. So it can do 4, 6, or 8 multiplications or sums per time, at a time, in parallel. On the left, you have a GPU, NVIDIA Quadro. You can perform, probably this chip has 64, 32, 180, 120, cores. Much simpler cores, but you can do 128 operations at a time in parallel. So it's much better for neural networks. And it's the first decision to make. Normally you use GPUs for neural networks, but you can also use standard computing power, the CPU, normally for doing tests or performing some prototyping, etc. Then we have the data pipelines. We need data to feed the network, and data is done by providing data itself. So we need the protocols, we need the database, we need the files where the data is stored. We need data cleaning, so we want to make sure that we are feeding the network with the right data. It's the same that when we filter the content to children in our lives. And we need data transformation because, you know, data is software. So in nature, everything is scaled. Everything around us is at our scale, or we can understand everything. But in the digital world, data can be larger, smaller. So maybe we can use a digital microscope to amplify data and make it more relevant or not. And this is what we mean by data transformation. Everything is related to preparing data to feed the network. And then finally, we have hardware, we have data, we need, of course, software. What kind of software do we need to build a neural network? Neural networks can be built by regular languages, programming languages, so Python, R, C++, whatever. But on top of them, we use libraries. Why do we use libraries? Because libraries have a lot of functions, a lot of utilities that we need to develop by software, and they have already prepared to implement the network. Some libraries even are graphical interface, so you just drag and drop and build the network, and all the software coding is done by the framework, by the application containing the library. We have some libraries, classical library. The first one, scikit-learn, is for learning purposes. You can download it here and make some basic neural networks for yourself to train, to understand the concepts, etc. It only has classic machine learning, of course, because computing power, you will do it in your computer and you will not be able to analyze very complex networks, but for doing some tests, it can be useful. Professional libraries are the next one: PyTorch, TensorFlow, Keras. Let me show them here. These frameworks are for building the network, training the network, and preparing everything into production. Okay, so we have PyTorch, we have Keras, we have TensorFlow, we have Microsoft Cognitive Toolkit, and they are used, as I said before, to define the model, so define the architecture that you want, to reduce code programming, as I said before, and to also, very important, to translate all the instructions into code specific for your CPU or your GPU. It's different, so depending on the hardware that you are using, you will need to adapt the coding to that hardware. And these frameworks precisely do that much more easily than by hand. Okay, let's show very briefly about TensorFlow. So TensorFlow is an open source library that is provided and sponsored by Google. So it's you may guess that it's the most common, is the largest vendor or provider in the world, and is used for training models in parallel, multiple devices using GPUs. So a lot of possibilities. Can build large-scale neural networks for deep learning and can be trained quickly. So it's a very powerful solution, and for this reason is the number one in terms of installations today. Then we have PyTorch. PyTorch is interesting because it is efficient for dynamic neural networks. So it works very well when you have challenges regarding the reconfiguration of the network. So self-supervising networks work very well with PyTorch. Then we have Keras. So Keras, probably, and this is my opinion, Keras is very powerful. So you can do a lot of configurations in Keras. And in fact, it uses TensorFlow as the backend, so it's a high-level environment that then translates to TensorFlow, and then TensorFlow does the rest of the work to run on the hardware. And it's very good if you want complex installations. So it's not for basic solutions or applications, is for ambitious projects. Okay, and then you have Microsoft Cognitive Toolkit. Microsoft is not the most famous framework for artificial intelligence, but it's probably an alternative to TensorFlow. Okay, so TensorFlow is Google, Microsoft, it depends on your preferences. Microsoft scales very well for very large hardware installations. The problem is, as I said before, it's by far the one with very little community, and you will find very little information about this platform. So you will be more or less alone with the Microsoft support only, and it's well, we need to see what will happen in the next months and years. This is a fast evolving ecosystem, so it depends on the amount of money invested by Microsoft in this toolkit. We will see it grow in footprint or not. Here we have a brief comparison of all the framework that we have shown. So the winners in ease of use is Keras and Microsoft. Regarding flexibility, PyTorch can provide very dynamic and complex networks, and regarding scalability, PyTorch and Microsoft are better than TensorFlow and Keras. But there are more, so you will find a lot of frameworks working for artificial intelligence. You have MXNet, you have Theano, you have Caffe2, you have Chainer, you have BigDL. BigDL is provided by Intel for your reference, so it's not the main one of the top engines or frameworks for artificial intelligence, but they work on Intel computers, on Intel CPUs. You have some obsolete or limited platforms like Torch. Torch was the origin of PyTorch, but Torch is much slower, much more limited. You have, for example, here DL4J is deep learning for Java. Is a specific framework to develop neural networks running on Java. It's not efficient at all. It's probably for demonstrative purposes of if you want to build a neural network that runs online on your website. You have different ideas, and it's possible that you will find much more than these ones. My recommendation is to go for the top ones. The secondary frameworks are probably good for specific applications, but you will never know if they will be alive in 2, 3, 4 years from now. And there are more software. There is more software that you will find around artificial neural network, machine learning, and deep learning, specifically deep learning. We have, for example, one important application that I want to highlight is Spark. Spark is owned by Apache, and is an analytic engine that provides easy, friendly environment to prepare data and provide large amounts of data to neural networks. So it's a complementary tool to improve the efficiency of the network by preparing data before it's fed to the network. And another one is Horbot. Horbot is an open source distributed deep learning framework specifically designed to run parallel network nodes running the network. Okay, so if you have a neural network to run a very complex task, and it cannot be run in a single computer or a single GPU, you can use Horbot to run in parallel in 3, 7, 10, 100 GPUs in parallel, and keeping your previous framework. So it works. You can see here it works with TensorFlow. It works with PyTorch. It works with Keras and some more. So you can use it for very large computing power requirements. And this is everything. We have reached the end of the presentation. I hope you liked it. It's been a bit long. If you have any question or any suggestion, I recommend that you follow my website and contact me, or you can add comments to this channel. I will be there answering everything you need. Thank you very much for your time, and I hope you enjoyed and know a bit more about machine learning, deep learning, neural networks, artificial intelligence today than before. Thank you very much, and goodbye.